Section: Introduction. We, as a group, are diving into the fascinating world of AI development, particularly focusing on creating AI systems that are not just good at collecting information through their senses but can also interact with their surroundings in meaningful ways. A major benefit of working on generalist AI systems is the ability to train a single neural network model across a wide range of tasks and types of data. This approach is highly efficient because it can be scaled up through more data, computing power, and adjustments to the model itself. Thanks to recent breakthroughs in general-purpose foundation models, we now have powerful new tools at our disposal for building AI systems that can take actions, moving us closer to achieving artificial general intelligence. However, despite their impressive performance on various AI challenges, these large foundation models often make mistakes, like imagining objects and actions that aren't actually there, and drawing incorrect conclusions. We believe a key reason for these errors is that these models aren't properly grounded. They're trained on vast amounts of internet data rather than in real or simulated environments. Moreover, the common method for creating systems that can handle multiple types of data involves using pre-trained foundation models for each data type without further tuning them. This means any mistakes in these models can end up in the final system, and without pre-training that includes multiple types of data, it can be hard for the system to understand information that spans different data types. To address these challenges, we're proposing a new way to train a model that can handle text, visual data, and actions all together. We start with pre-trained language and visual language models to give our system a strong foundation, and then we train it further in a unified way. We call our approach in the model it produces an interactive agent foundation model because it's designed to interact with people and its environment and understand both visual and language information, as we demonstrate. In this paper, we're excited to share our findings from training a model with 277 million parameters on 13.4 million video frames from various sources. This model can interact in environments using text, video, images, dialogue, captioning, visual question answering, and even actions, across 4 different virtual settings. We tested our model in 3 areas: robotics, gaming AI, and healthcare, and found it could adapt its skills across all these domains. We're looking forward to sharing our code and models with the research community to help advance this field. In the related work section, we discuss the background of our research. Foundation models have been a big focus, with efforts to train them on a wide range of internet data. In natural language processing, this includes both large proprietary models like the GPT series and smaller, open-source ones. In computer vision, self-supervised learning methods like masked autoencoders and contrastive learning have been popular. Recently, there's been a lot of work on multimodal models, which aim to connect large pre-trained visual and language models with a relatively small number of parameters. Unlike most previous efforts, we're exploring how to train models to understand visual and action-based information alongside language, specifically for tasks that require the AI to take action. Agent-based AI, which focuses on creating dynamic behaviors based on understanding the environment, has seen significant advancements through the use of large foundation models. This includes improvements in how robots interact with their surroundings and with people, as well as in navigation and manipulation tasks. In gaming, agents need to understand both visual scenes and text instructions. In healthcare, there's been a focus on text-based interactions between humans and AI, with applications in diagnostics, information retrieval, and monitoring. Section summary. The goal of AI researchers is to develop generalist AI systems that can gather sensory information and interact meaningfully with their environments. However, current large foundation models frequently produce incorrect information and hallucinate due to a lack of grounding in their training environments. To address this, a unified pre-training framework is proposed to handle text, visual data, and actions as input, resulting in an interactive agent foundation model capable of engaging in interactive multimodal settings across domains such as robotics, gaming AI, and healthcare. The proposed model is pre-trained across various data sources and domains, enabling it to effectively engage in interactive multimodal settings using text, video, images, dialogue, captioning, visual question answering, and embodied actions within virtual environments. Additionally, the model demonstrates generalization abilities across disparate domains such as robotics, gaming AI, and healthcare, and the code and models will be released publicly to facilitate further research in this area. Section: Agent Paradigm. We're at an exciting point in time where advancements in artificial intelligence, AI, have made it possible for machines to understand both language and visual information from the real world. This has sparked a lot of interest in creating robots that can work in unpredictable environments, moving beyond just simulations. Imagine a robot that can start interacting with people who aren't tech experts and quickly learn to do household chores right out of the box. In this part of our discussion, we introduce a new way of thinking about these robots, which we call embodied agents, and explain how our interactive agent foundation model fits into this new approach. We describe embodied agents as intelligent beings that can act on their own by interpreting sensory data, whether they're in the real world, a virtual setting, or a mix of both. These agents are seen as part of a team, working alongside humans, understanding and communicating through language and visuals, and performing actions based on human needs. This way, they can help reduce the burden of tasks in both virtual and real-world settings. For these agents to work effectively, we believe they need three main things: the ability to perceive their surroundings in detail through multiple senses, much like humans do; the ability to plan, especially for tasks that require moving around or manipulating objects, which relies on good perception and interaction skills; and the ability to interact smoothly with both humans and their environment, making tasks more efficient and effective. Our interactive agent foundation model is an early step towards creating such agents. It focuses on these essential aspects, aiming to build a practical helper system. However, creating an embodied agent is challenging due to the complexity of real-world interactions and the need to understand a wide range of objects and natural language instructions. To tackle these challenges, we're bringing together experts from various fields. Our approach combines visual understanding with language processing to give robots a more intuitive grasp of their surroundings and better decision-making context. We're developing a system that can process both images and videos alongside language, which helps in several ways. It allows for a broader training dataset, improves performance on various tasks, and reduces the size of the model, making it more practical for real-world applications like robotics and interactive healthcare. In terms of technical details, we start with two pre-trained components for visual and language processing. We then train our model to predict actions or text based on visual inputs and text prompts, incorporating information from previous actions and visuals to improve predictions. This process involves a lot of data and careful training, especially to handle visual information effectively. Our method aims to make the model more versatile and efficient, which is crucial for applications where computing resources are limited. In summary, we're working on a model that can understand and interact with the world in a way that's similar to humans, using both visual and language cues. This is just the beginning, and there's a lot more to explore and develop in this exciting field. Section Summary. Recent advancements in AI technology have led to a shift in interest towards practical applications of embodied agent technology in uncertain environments. The embodied agent paradigm is defined as an intelligent agent capable of autonomously taking suitable actions based on sensory input, whether in the physical world or in a virtual environment, and is expected to mitigate tasks in both virtual reality and the physical world. The proposed interactive agent foundation model aims to develop an embodied agent that functions as a practical assistance system, focusing on multi-sensory perception, planning for navigation and manipulation, and interaction with humans and environments. The proposed framework combines visual perception with linguistic understanding to endow robots with a more intuitive understanding of their surroundings and better contextual reasoning, with a focus on joint image and video encoding to enhance model capabilities across various tasks. The model architecture involves initializing the model with pre-trained modules, training linear layers for cross-modal information sharing, and incorporating prior time steps into the model during pre-training. Section: Pre-training strategy. We start by training our model on a diverse set of tasks related to robotics and video games. Each piece of data we use includes instructions written in text, video clips, and specific actions that were taken. We organize each piece of data into a sequence that includes the text instructions, sequences of images from video frames, and the actions associated with those frames. Imagine this as a list that starts with the text instructions, followed by alternating video frame images and the actions taken in those frames, all the way up to the total number of frames we're considering. For the text instructions, we break them down into individual pieces called tokens, and we refer to the settings or parameters of our model as theta. When we train our model, we focus on improving it in three main areas: understanding and generating language, reconstructing images accurately, and predicting actions correctly. To improve language understanding, we use a common approach where the model tries to predict the next word in the instructions based on the words that came before it. This helps in minimizing errors in understanding the text. For images, we randomly hide 75% of the parts of the image and then challenge the model to recreate the original image from the remaining visible parts. This process helps the model get better at understanding and reconstructing images. When it comes to actions, our goal is to make the model good at predicting the next action by considering all the information it has, including the text instructions, the images, and the previous actions. We combine these three areas into a single measure to see how well the model is doing overall. For tasks involving robotics, we only look at 4 frames of video since the tasks don't need a lot of historical data to predict the next action. But for video game tasks, we use 9 frames because having more background information helps in making better predictions. We believe that training a model like this, which understands visuals, language, and actions, can be very powerful for a wide range of interactive tasks. We tested our model on 3 main areas: robotics, where it helped in manipulating objects based on language instructions; video games, where it interacted in a virtual environment; and healthcare, where it assisted in understanding and interacting in medical settings. We fine-tuned our model with specific data for each of these tasks and found that it performed well in predicting actions, understanding visuals, and interacting based on natural language. For the robotics tests, we used 2 datasets where robots performed tasks based on language instructions. One dataset involved rearranging objects on a table, and the other involved more complex manipulation tasks. These tests helped us see how well our model could handle different levels of instruction complexity and task length. In the gaming area, we used a dataset from Minecraft, where players had no specific goals but their actions and the changes in their inventory were recorded. We used a newer version of GPT to label these videos with more specific instructions, which helped in understanding the gameplay better. We also used a dataset from a multiplayer game called Bleeding Edge, applying the same technique to label the videos. This approach helped us train our model to understand and predict actions in a gaming context. Section Summary. The pre-training strategy involves training the model on a variety of robotics and gaming tasks, with each input sample containing text instructions, videos, and action tokens. The loss function for each sample includes language modeling, masked image auto-encoding, and action modeling components, and the model is fine-tuned for specific datasets in robotics, gaming, and healthcare scenarios to demonstrate competitive performance in action prediction, visual understanding, and natural language-driven interactions. For robotics tasks, the model is tested on language-guided manipulation tasks using the language table and Calvin datasets, while for gaming tasks, the model is evaluated on Minecraft and Bleeding Edge gameplay datasets. Section: Healthcare tasks. In the healthcare area we mainly used data from real-life recordings in hospital ICU rooms, captured by cameras mounted on the walls. Experienced ICU nurses wrote descriptions for short video clips, about 5 to 10 seconds long, showing typical nursing tasks in the ICU. We also gathered detailed nursing notes on key observations made over longer periods, from 5 to 30 minutes, which included vital clinical measurements that help in evaluating and treating patients. Our study particularly focused on 2 things: the RASS score, which measures how agitated or sedated a patient is, and the bed's position to ensure it's angled correctly to reduce the risk of pneumonia from ventilators. These assessments are often recorded in medical records, and automating this process could help healthcare workers save time. To better tailor our model for understanding human interactions in the ICU, we used the descriptions and clinical notes provided by nurses to create a new set of video questions and answers with the help of GPT-4. This new dataset, which doesn't include any private patient information, can be shared widely to help train other clinical models that work with language. We looked at 3 main tasks: creating captions for videos, answering questions about videos, and predicting RASS scores, which we treated as a problem of recognizing certain activities. For more technical details, we're working on a general-purpose AI model that can process various types of input and respond appropriately in many different situations. We tested our model not just in healthcare, but also in robotics, gaming, and other interactive tasks. To get our model ready, we trained it on complete datasets from Language Table, Calvin, Minecraft, and Bleeding Edge for 100 cycles. We adjusted the learning rate over time starting from a very small number, and we set up the model's vision part using a base model called Clip with a specific setting, and its language and action parts using another model called Opt125M. The training used a significant amount of computing power and time. We also customized the model for each task by adding new action tokens for the actions in our training data, including specific tokens for starting and ending actions. For example, in Minecraft, we added tokens for 23 button actions and divided mouse movements into 100 parts each for horizontal and vertical movements. For robotics tasks, we added tokens for different actions a robot could take and for the state of the robot, including where it's moving. Our datasets were quite large, with millions of frames from video game and robotics tasks. To help the model learn better, we also altered the images slightly during training by adjusting their brightness, saturation, and hue. Finally, we fine-tuned our pre-trained model on specific datasets for robotics and evaluated its performance, using the same methods and settings as in the initial training phase. Section Summary. In the healthcare domain, the study utilized real-world ICU video footage and nurse-generated captions to train a model for recognizing nursing activities and predicting patient conditions like agitation and bed position. The model was fine-tuned using GPT-4 to generate a synthetic video question-answer dataset, which didn't involve any patient data and could be publicly available. Additionally, the research involved pre-training a generic AI model using diverse interactive environments and specific tasks like robotics manipulation, game playing, and interactive healthcare tasks, with detailed experimental settings and results provided. Section: Language Table. In our study, we explored different datasets and tasks to fine-tune and evaluate our model's performance. Let's break down our approach and findings in simpler terms. Starting with the language table dataset, we worked with data from an experiment that included 8 blocks, but only 2 of these blocks were relevant to our tasks, generating over 181,000 sequences of actions. We then broke down these sequences into smaller parts, called frames, to fit our model, ending up with more than 1.2 million pieces of data for fine-tuning. We tested our model on 5 specific tasks, like moving blocks around in various ways or separating them, and checked how well it did by averaging the success rates from 50 randomly chosen sequences for each task. Although our model did better than starting from 0, it didn't outperform all other models, possibly because we used less data for training it initially. In the Calvin dataset, we took long sequences of actions and also split them into frames, this time getting over 360,000 samples across 34 tasks. We chose to use images from a third-person view camera to give our model a better overall picture of the scene. We included all different appearance settings in our fine-tuning process to make our dataset bigger, following a specific task definition. To see how well our model did over multiple steps, we averaged the success rates, finding that our model performed better than another method, multi-context imitation learning, even though we used only 1% of the data. For gaming experiments with Minecraft and Bleeding Edge, we looked at how well our model could predict actions from video frames and instructions, and how accurately it could reconstruct actions, using a metric called May. We tested our model on 100 videos from each game that were not used in training. Our findings showed that fine-tuning our pre-trained model worked much better than starting from scratch in both games, emphasizing the value of our diverse pre-training data. We also compared our model's action predictions to the actual actions to visually show how well it did. In the healthcare experiments, we tested our model on 3 tasks: creating captions for videos, answering questions about videos, and recognizing activities to predict RASS scores. We used a specific setup for each task, like using the question as a prompt for the visual question answering task. We compared our model's performance to 3 other approaches that also used pre-trained models but in different ways. Our model was trained on video clips and evaluated on its ability to understand and describe healthcare-related activities. For all these experiments, we trained our model for a set period on powerful computer hardware without tweaking it too much to keep the comparison fair. Our findings across different datasets and tasks highlight the effectiveness of our model, especially with its diverse pre-training and its potential applications in various fields, from gaming to healthcare. Section Summary. In the language table dataset, we utilized 181,020 trajectories from 8 blocks, with 1,233,659 samples for fine-tuning, and evaluated the model on 5 different subtasks, showing that the pre-trained model outperformed training from scratch but was surpassed by other models due to using less pre-training data. In the Calvin dataset, we used 360,566 samples across 34 tasks for fine-tuning, achieving better performance compared to multi-context imitation learning, MCIL, while using only 1% of the data. Additionally, in gaming experiments, our pre-trained model showed significant effectiveness in fine-tuning compared to training from scratch for both Minecraft and Bleeding Edge, emphasizing the importance of diverse pre-training. Section: Pre-training loss curves. We've created graphs to show how our training process, which combines different types of learning, changes over 100 rounds of training. You can find more detailed breakdowns of this process in the appendix of our paper. When we compare our model to GPT-4v, it's clear that our model is much better at predicting specific actions and movements. On the other hand, GPT-4v tends to give more general instructions without getting into the details of the actions needed. We also looked into how effective our method of training the agent from the beginning is, especially when compared to starting from scratch or using a similar method to what's used in visual language models like LLAVA or Mini-GPT-4. These comparisons are shown in 2 tables in our paper. Specifically, we found that the common practice of fine-tuning visual language models with fixed visual encoders doesn't work as well as our method for recognizing actions in healthcare scenarios. Moreover, our way of training the agent from the start improves its ability to predict actions in various situations, including games and robotics, across all the datasets we tested.